scientific notation. It's a pretty cool thing. So I asked you to predict what you thought this might mean. And scientific notation is a way that scientists write. And it's a way for them to write really big numbers like the distances between stars, or really tiny numbers like the size of a red blood cell in your body. So they have a special way that helps them write really big numbers. So first we just practiced powers of 10, and I said for you to figure out how many zeros were in the decimal number for 10 to the 6th power, and you all remember that it's got 6 zeros, it's a million. And then how many zeros are to the right of the decimal when I write 1/1,000,000th? And we had to review that when I'm on the right side of the decimal, this 1 takes up one of the place values, the millions place, so it's 5 zeros. But how many decimal places are there in the decimal notation? 6. So that -6 matches the 6 decimal places that I have when I write 1/1,000,000th. Then we reviewed, how do I write 10 to the power of -6 as a fraction? Well, remember, it's the reciprocal of 10 to the 6th. So if I write 1,000,000, I just put it under a 1. So this is the fraction. But I can also show the reciprocal of this by leaving that 1,000,000 in scientific notation. So it's 1 over 10 to the 6th. And then you practice that with 10 to the -12th. And remember that this is 10 to the positive 12th is a trillion. 10 to the -12th is 1 over a trillion, and that's 1 over 10 to the 12th, which is a positive exponent because we already took care of the negative by kicking it downstairs in the fraction and putting it under a 1. So this is an example of a number in scientific notation. There are 3 parts to it. So the first part is you have to have a number that's bigger than 1 but less than 10. 3.45 is bigger than 1 but less than 10. Then you have to have a multiplication symbol. It can either be this multiplication symbol or the raised dot. And then you have to have a power of 10. So a power of 10 is either 10 to a positive exponent if the real number is bigger than the decimal 3.45, or a negative exponent if the real number is smaller than the decimal part of it, 3.45. Well, this scientist is working with really small things, and I can tell that because it's 3 4500 times 10 to the power of -2. So the real number I find by moving the decimal 2 places to the left. So this scientist is dealing with something that is 345 10,000th of 1. So it's a tiny, small number. And then again, we talked about why is it called scientific notation? Again, it's a way that scientists write really small numbers or really big numbers. So here was an example. The speed of light is very fast. So if you traveled at the speed of light and it bent around the planet Earth, light could travel about 8 times around the planet Earth in 1 second. That's the time it takes you to say 1/1000th. 5,900,000,000,000,000 miles is the distance that light travels in a year. It's a really big number, and the question was, how do you write it in scientific notation? So the first thing you have to figure out is, where do I put the decimal in this number? So I have a number that is bigger than 1 but less than 10, and this is the only place I can put it. If I put it in front of the 5, it's less than 1. If I put it after the 9, it's bigger than 10. The only place I can put it here. So the decimal part is 5.9. multiplied by a power of 10. And the way I know it's 10 to the 12th is because this real number is big. And so I have to move the decimal from 5.9 12 times to the right to get back to the real number. So that is times 10 to the 12th. And then we practice some more. So the area of the Earth in square miles is 196,950,000 square miles. To put that in scientific notation, we have to put the decimal here. 1.9695 times 10 to the 8th power, because when I put it here, I have to move it 8 times to get it back to the real area of the Earth in square miles. Then we have this super teeny tiny fairy fly. It only weighs 5/1,000,000th of a gram. A gram is about the mass of a grape. So to figure out what this is in scientific notation, I have to know that the only place I can put the decimal is after the 5. So I put it here, and I put 5.0 just to be clear that there's nothing in the tens place. And then I ask myself, to get back to the real number, if I put the decimal here, how many times do I have to move it to the left? And it's 6 times. So this number in scientific notation is 5.0 times 10 to the power of negative 6. Remember, that's 1 millionth, and 5 times a millionth is 5 millionths grams. Okay, then you had your slates, and we practiced these in class with your groups on your slates, and you had to change this. So this number is the number of seconds in a week, 604,800 seconds in a week in scientific notation. The decimal must go after the 6, and it's times 10 to the 5th, because I would have to move it 5 times to get back to the real number, to the right. The thickness of a piece of paper on a Post-it pad in inches is 39 ten-thousandths of an inch. So to put that in scientific notation, I must move that decimal 3 times to get 3.9. But the real number is 1/1000th of that. So it's times 10 to the power of negative 3. Go the other way now. So then we took the average radius of the Earth in scientific notation, and we changed that to decimal notation. Well, I need to move the decimal 6 times to the right. 1, 2, 3, 4, 5, 6, which is 6,380,000 meters. Because remember, this is a million, so it's a million times bigger than that, because that's a multiplication. And that was in meters, and I said to the class, that's a small unit. If I change that to kilometers, I can picture this distance better. So to change meters to kilometers, we had to divide by 1,000, because every kilometer has 1,000 meters in it. And the best way to do that is to divide both of these by 1,000 by taking off 3 zeros, which is really moving the decimal 3 times to the left. So that's equal to 6,380 kilometers. And this is the radius of the Earth, the center of the Earth to the Earth's surface. And you practice some more. The thickness of a wire on a computer chip in meters is really tiny. So it's 3.0 times 1/1,000,000th times 10 to the power of negative 6. So we take the decimal and we move it 6 times to the left because it's tiny, and we get 3 millionths of a meter. And then we said, how many centimeters is that? Well, every meter has 100 centimeters, so we multiplied by 100, which is just moving the decimal twice to the right. And now we get 3/10,000th of a centimeter, and that's still awfully little, so we change that to millimeters. Every centimeter has 10 millimeters, so we multiply by 10, and we get 3/1000th of a teeny tiny millimeter. So these wires on computer chips are very, very small. Then we had a rate of the speed of sound in the air. Sound travels much more slowly than electricity or light. It's only about 720 miles per hour. So the rate in centimeters per second in scientific notation is 3.43 times 10 to the 4th. So to change that into the rate in air, we move the decimal 4 times to the right. And that means I have to put in 2 zeros, and that was 34,300. Let's see if I can write this. 34,300 centimeters per second. So that's the speed of sound in the air, centimeters per 1 second. And then we talked about railroad tracks and how when the temperature increases, for each degree rise in Fahrenheit in temperature, the length of the steel in a railroad track increases in centimeters. And that's why they have to put joints in the track, because otherwise the railroad track would buckle. So what is this in centimeters? And you guys were getting really good at it. You knew I had to move the decimal 5 times to the left. 1, 2, 3, 4, 5. I have to move it once to the left to get it in front of the 1, which means I have to put in 4 more placeholders of zeros. And so that is this number, 0.0000012 centimeters. That's 12 millionths of 1 centimeter. So it's a pretty tiny amount. And then we just talked about, gee, what would it be if it rose 30 degrees? So I was showing you how you can do this in your head. 30 is 3 times 10. So to multiply by 10, we just move the decimal once to the right. And then 30 is 3 times bigger than 10, so we just tripled that. So if the temperature rises 30 degrees Fahrenheit, then that's how much longer the steel gets in centimeters. Still a small amount, but it still could make a big difference. All right, and then we worked with the number of passengers a day in 1998 in Chicago, and it was this number in scientific notation. And, excuse me, this was in a year. And I had you figure out the number per day. So I taught you how to enter this in your calculator. And the long way is to do 3.47 times 10 to the power of 7. But I showed you in your scientific calculator, most of you have an EE key or an exponent key. And if you just put 3.47 and hit that key with the whatever the power of 10 is, 7, it automatically will take you to the decimal notation of the number. And then we had to figure out, gee, if it's this many people in a year, what is that per day? And you guys divided by 365 days in a year. And we got it's about 95,000 people per day that go through that airport, which is a lot. This was 34,700,000 people per year. And that's a lot of people in a year. That's really just a little bit less than a tenth of the population of the United States. So you have to know what your scientific calculator does. If yours has the EE or just one E, this is what it means. If yours has EXP, this is what it means. So we found out what yours said, and most of the classes' scientific calculators are new, and they actually give you the number in scientific notation in the proper form, which is pretty cool. All right, and then I had you enter in some calculations until we got to a number that your calculator could not display. And this was the answer to that in scientific notation. Some people's calculators said 3.15, oops, there's a 3 in there, 36 E15, that means this. Some of yours said there was no times 10, it just had this 15 written as an exponent, but that means times 10 to the 15th. All right, and then we corrected this homework, and this is tonight's homework. So you may choose the basic or the challenge.